Testing a claim about a population mean is one of the most important methods presented in the book. Section 8.3 deals with the very realistic and commonly used case in which the population standard deviation sigma is not known. We are going to focus our time in this chapter on this scenario. Section 8.2 describes when the population standard deviation is known, but if the population standard deviation is known, then it is likely that we already know the population mean, because the population mean is used to calculate the population standard deviation. Population standard deviation is defined to be the average distance from the mean. So we have to know the mean to calculate the standard deviation. So for us right now, Section 8.2 is not going to be as important as Section 8.3. But the big picture between the two of them is that when the population standard deviation is not known, we're going to use the t-distribution, just like when we were doing confidence intervals in Chapter 7. And then similarly for Section 8.2, when the population standard deviation is known, in this case, we would use the normal distribution, okay? So just like for our confidence intervals, we're going to use the same distributions depending on what we are given, what we know, for hypothesis tests. So let's talk about the t-test for a mean. Just like confidence intervals for a mean, when the population standard deviation is unknown, we can use the t-distribution to conduct a hypothesis test. We have our formula here for our test statistic. T equals the sample mean minus the population mean divided by the sample standard deviation over the square root of the sample size. So this calculation is what we call the test statistic in our hypothesis test. And now, just like we talked about in the first section, there are two different procedures that we can use for our hypothesis test. We can do what's called the traditional method, which compares the test statistic to a critical value, and then if the test statistic is in the rejection region or not. Or we can do what's called the p-value method, which takes the probability that the test statistic would generate and compares that probability to our significance level, alpha. Both methods will yield the same result, so it does not matter which method we use. And I will be demonstrating both as we go through the example so that you are able to see both methods in action. Requirements for the t-test: we have to have a simple random sample, and we either have to have a normally distributed population or a sample size greater than 30. So those things are important. The population is normally distributed if n is less than or equal to 30. Our sample size is less than or equal to 30. We have to have a normally distributed population. Or we have a big sample size, n is greater than 30. And we've got some steps here. We're going to draw the figure, find the critical region, determine what type of test we have, if it's a left-tailed test, a right-tailed test, or a two-tailed test. And remember, that's all based on the inequality in our claim. Then using the degrees of freedom, just like Chapter 7, degrees of freedom for t, n minus 1, we'll find the critical t value based on our significance level. And then these three pictures given to show you the differences that we have. So in part A, it's a left-tailed test, so we're going to have mu is less than some value that I'm going to call m. I don't know what it is, so I'm just going to pick a number at random, m. So mu is less than m. This is our alternative hypothesis. And then our critical value here separates the rejection region from the non-rejection region. So rejection region on the left, non-rejection region on the right. If we're doing a left-tailed test, we would find the test statistic and then determine where that test statistic falls on the number line in relation to the critical value. Again, we'll walk through this with real numbers, but just trying to get you used to this idea. Similarly, for a right-tailed test, our alternative hypothesis would be mu is greater than a number, which means our critical value over on the right, rejection region to the right, non-rejection to the left. And then a two-tailed test. For a two-tailed test, instead of having one single rejection region, we have two pieces, one on either side. And that's because for our alternative hypothesis, we have the mean is not equal to some number. And since it's not equal, it could be lower or it could be higher. If it's too far away than the value we think it is, then our test statistic is going to sit on one of the sides of the mean. Remember, the mean is here in the middle. And then we have the non-rejection region here in the middle. So for finding critical values for a t-test, this I just want you to get used to using the t-distribution function in Google or Excel. And we've got three different scenarios, a right-tailed test, a left-tailed test, and a two-tailed test. We know n, and we know our significance levels. I will work through two of them, and I'm going to leave the third one for you to try, and then come back and check your answer on the OneNote. So we'll do the right-tailed test and the two-tailed test, and I'll leave the left-tailed for you to try on your own. So let's start out with a right-tailed test. So what this means is I've got a t-distribution here. Alpha is 0.01, so up here in the right tail, I have 0.01 area. I'm looking for this critical value that separates that 0.01 rejection region from the non-rejection region. And it's a right-tailed test, so we're going to do area to the left would be t.inv, 1 minus alpha, so 1 minus 0.01, because I need the area to the left when I'm doing these formulas. I am given area to the right for a right-tailed test. Degrees of freedom are going to be 19 minus 1. So degrees of freedom, 19 minus 1 would give me 18. You can either put 18 in there or you can type out 19 minus 1 and make Excel calculate it. It's totally fine. I'll just do it right here in Excel. So t.inv, it wants a probability. So we can either type in 0.99 or make Excel calculate it, 1 minus 0.01. And 19 minus 1 is 18 for our degrees of freedom. And we end up with 2.552. So this critical value, 2.552. And just so you know, this diagram that we have, this is a t-distribution, so the mean is going to be 0. And we have this critical value, 2.552. Now let's take a look at the two-tailed test as a comparison. So for the two-tailed test, I'll draw my t-distribution again, 0. Two-tailed test means I've got one on either side. So I've got area on either side. And alpha being 0.05 means that in each of the tails, I have 0.025 area. We're going to split that alpha in half. N is 15, so degrees of freedom will be 14. And we can form our t.inv. I can either find the negative value and then change it to positive, or I can find the positive value and change it to negative. I don't have to run this calculation twice. Whatever I get for one, the other one, the sign is going to be opposite. The t-distribution is symmetric, just like the normal distribution is, which makes this really nice. So if I put in t.inv, let's just use 0.025, half of 0.05. You could also put in there 0.05 divided by 2 and make Excel calculate it. And then our degrees of freedom, 14. And then let's see what Excel will give us. So I have t.inv. I'm going to put in 0.05 divided by 2, make it calculate it. And then our degrees of freedom, 14. And we hit enter and we get negative 2.1447, 2.145. So negative 2.145. So that would be one critical value. And then the other critical value is the same absolute value. Just change the sign to positive. So we'll have two critical values here. And the idea with either of these scenarios is once we get our critical value, then we calculate the test statistic and we figure out where that test statistic sits. Now, the template will do a lot of the work for us. But I do want to see your diagrams just like this. I want to see you draw out the distributions, Put the critical values on there, put the test statistic on there so that you're understanding the connections between what the numbers are and then what the conclusion is. So remember, this is about interpretation. Even though the template will give you all of the answers, I want you to interpret those answers. Explain to me why it says to reject the null hypothesis or to fail to reject the null hypothesis, and use these pictures to help justify that claim. So in the next part of our lesson, we'll work with a full hypothesis test for means.